Yeah, g'day, it's Charlie, ZL2CTM. So I just want to spend this video looking at the RF amplifier. So that's the amplifier that's going to be sitting between the antenna and the bandpass filter. So for something different, I decided to use, based on one of the recommendations from a previous video in the comments, an MPSA 10 transistor. That's a VHF/UHF transistor. So I was sort of hoping that the gain bandwidth product would be quite a bit higher than, say, a 2N3904, and as a consequence might afford a little bit more gain at the frequency of operation. So just for something different, just using this particular device here. The configuration for the amp, just a common emitter with voltage divider biasing, and we'll look at in a sec a couple of options there for the collector circuit, but ultimately as a starting point to have some kind of impedance matching transformer between the collector and the load. And at this stage, having the amplifier running flat out, so in other words, having that emitter resistor fully bypassed to try and maximize the gain. Hanging off VCC there is just a stock standard 100 nanofarad or 0.1 microfarad capacitor and 100 microfarads there. Yeah, good. Right, so in terms of the device itself, so based on the spec sheet, a lot of the maximums for the beta and HFE and all sorts of figures was all based around 4 milliamps. So just for the sake of it, I'm going to set my quiescent current through this device at 4 milliamps. The gain bandwidth product is sitting at 650 megahertz, and I'm just going to design around 3.7 megahertz, and then whatever the amplifier will be at 7.1 or that sort of 40 meter band, it'll be. So 650 divided by our operating frequency, in this particular case for the design of 3.7 megs, gives us 185.7, which we'll use for working out the various components. So the emitter resistor, that resistor here, so we'll just use a normal rule of thumb that the voltage at the emitter will be a 10th VCC. So to work out that particular resistance there, 13.8 volts times a 10th divided by the current through it, or 4 milliamps, comes out at 345 ohms, so we'll go with a standard value of 330 ohms. R2 there, that's the bottom resistor there in the voltage divider biasing. So the voltage at the base will be the voltage at the emitter plus 0.7 volts. So that voltage there, and just using Ohm's law divided by the current through there, we'll be able to resolve or solve for R2. So 1.38, so that's our emitter resistor. I say again, our voltage at the emitter, a 10th VCC, plus 0.7, and then again for a nice stiff voltage divider there, so any kind of fluctuations in the transistor or the like, nice and stiff, we'll have 10 times the base current flowing through R2. So 10 times 4 milliamps divided by beta, 185.7, comes out at 95, so again 96.56, so we'll use 10k. R1, that's the top resistor there, so that's going to have 10 times running through there, as well as one lot of base current, so there'll be 11 times the base current going through that one. So as we see here. So again, Ohm's law, it's going to be the voltage at that point, which is 13.8, minus the voltage at that point, which is going to be emitter plus 0.7, divided by the current through. So exactly what we see here. So 13.8 minus our emitter voltage plus 0.7, divided by 11 times our quiescent current divided by 185.7, comes out at 49.463, so we'll just use 47k ohm as the nearest standard value for that. For our coupling capacitor coming in, it'll work out to be roughly 100 nanofarads, but again just double checking, so we want to be less than 100 ohms at 3.5 megahertz, so our lowest frequency of operation. Why our lowest? Because XC equals 1 over 2 pi FC. So our lowest point will result in the highest amount or the greatest amount of collector my apologies, capacitor reactance. So that's why we use that 3.5 megs there. So substituting in, so bringing our C up there and bringing XC down the bottom, 2 pi 3.5 times 100 ohms comes out at 354 picofarads, which is pretty close to 1 nanofarad. So I think we'll just use with our standard 100 nanofarads or a 104. Again, any increase in the bottom of the right hand side will result in a decrease in our capacitor reactance, which is in the right direction. Right, and as a starting point for our emitter bypass capacitor, I'm going to start off by using 100 nanofarads. But I note using LT Spice, I've said try there. With LT Spice I'm going to have a bit of a play around with that value there to see if I can somehow make this amplifier here perform a little bit better across the band from 3.5 megahertz through to 3.2, or the top of that 40 meter band. Right, so I do want to try and match our antenna, which is going to be 50 ohms with our input resistance of the amplifier. So Rin should be approximately R1 in parallel with R2, that's our voltage divider there, in parallel with beta times little re plus big Re, where little re equals 26 divided by our emitter current in milliamps. And our big Re, because it's been fully bypassed by that emitter capacitor, will become to 0. So 47k in parallel with 10k in parallel with 185 times 26 divided by 4 comes out at roughly 1049 ohms. So I need a transformer which is going to transform our antenna, our 50 ohm antenna, up to 1049 for maximum power transfer between our antenna and our amplifier. You'll notice in the past I have played around with artificially setting Rin to be roughly 50 ohms by making Re there very small. And by making Re there very small was by having quite a high emitter current. And in the past I have played around with values, if I recall, up or around 42 milliamps. That resulted in a power dissipation of the transistor that was still within the limits called out in the specification sheet, but did make it run quite warm. So for this one here, I decided to do something different and design an input transformer to, like I say, transform that 50 ohms through to 1049. So working out our our turns ratio, noting that 50 times n squared, once we need to get 1049, so we can solve for n. 1049 divided by 50, take the square root, comes out at 4.58, which is pretty close to 5 to 23 as a turns ratio. So 23 divided by 5 is pretty close to 4.58 in that particular case. And we just want to double check too that the inductive reactance, or our XL, of the smallest side of that transformer, which will be 5 turns, we want to make sure that its XL is roughly that sort of 4 to 5 times the load it's seeing, so 4 to 5 times 50. So how do we do that? So 5 turns on an FT37-43 gives us 8.75 microhenries. And noting that our inductive reactance equals 2 pi FL, we can substitute in XL equals 2 pi, our frequency, so 3.5 megahertz, times, that's our lowest frequency, remember, so we want to go to keep the low end to make that the worst case. If that was 7.1, then naturally that would be higher. So our lowest frequency of operation, so what do we say, F times L in this particular case is 8.75 microhenries, comes out 192 ohms. And 192 ohms is approximately 4 times 50, so we're not too far off there. Another option is, and probably a better option, is to run with 6 to 27, so 27 divided by 6, again gives us approximately 4.58. Repeating exactly the same process, 6 turns on an FT37-43 gives us 12.6 microhenries, which results in an XL of 277 ohms, which is close to 5 times 50 ohms. So I'm going to run with this one, the 5 times 50, and that's 6 turns. Is if you've made enough of these radios, it's quite a common turns ratio for certainly for me with the 80 meter band. So in other words, I need to make a transformer which is 6 to 27. The 6 turns will be on the 50 ohm side, and the 27 turns will be on the input to the transformer. Right, so that leads on to the output circuit, and based on some comments that came through from Lars Thompson, I remember reading this and I'd forgotten about it, and he reminded me, so I went back and read it again. And as we know, if we look at the output of, let's say, a signal generator, or in this particular case it's our amplifier, there is some collector impedance here, or resistance if we don't have a reactive component. So if we were to measure, if I can just find the pencil, if we were to measure open circuit at this point, then there's no current flowing, so therefore there's no voltage drop across this internal impedance, so therefore the voltage here would be the voltage essentially at the output of our amplifier. If we now connect a load and still measure off this point, and if we were to adjust R to be the same value as this unknown collector impedance, when we get to a point where that voltage is now our original voltage divided by 2, then we know for sure that R equals this value over here. So if we now take this out of circuit, in other words disconnect it, measure, put across an ohm meter and measure that, then that equals that. So that's essentially exactly what I've done here. So what I elected to do for a start is I threw a 10 microhenry choke into the collector circuit. I had to do a DC isolation here so we didn't short the collector to earth through that 1 k ohm resistor there, so just threw in a nice 100 nanofarad capacitor there, and I measured the voltage there. So I took that, and that equaled V. I then connected a 1 k ohm trim pot, and still measuring at that point, adjusted it to equal V divided by 2. As I see it, so that's what I'll try to write down here. Open circuit voltage divided by 2 came out to be a value of 326 ohms. So with some confidence I can say that our unknown collector impedance here, annotated up here, is roughly 326 ohms. Okay, so that's great. So I want to match then that 326 ohms at the collector to my 50 ohm load. So I need another transformer here. So again, working out N, 326 divided by 50 square root, comes out at 2.55, which is pretty close to a turns ratio of 15 to 6. Note the 6 there, that's a nice value there, because I can say with some confidence based on our previous calculations that 6 turns at 3.5 megahertz is going to give me an XL of roughly 5 times 50. So again, we're just looking at the smallest side of that particular transformer there. What I then did, and you'll recall that that was my original thinking, was just to have a transformer in the load. I then elected just to take that same transformer, that 15 to 6 that was over here, and throw it straight into the collector circuit just to try and work out what was going on. Did a very similar approach that Lars pointed out. Again, measured the open circuit voltage here. I then put a 1 k ohm trim pot, much the same as this up here, and repeated the process to work out what that open circuit voltage divided by 2 would be in regards to that resistance. And lo and behold, probably more sheer fluke than anything, that it turned out to be 50 ohms. So in this particular configuration, which is the current configuration in the test amplifier, I've got that 15 to 6 transformer in the collector, and over here is our 50 ohms. And and I'm getting what should be, hopefully fingers crossed, maximum power transfer. The option that Lars talked about was just throwing in here. You could initially think about that 200 ohms there. You're trying to present 200 ohms to the collector from a 50 ohm load, but in his experience, and arguably here as well, that assumption doesn't necessarily hold true in reality. But you could just go ahead and throw a transformer in there, take your open circuit voltage, put a variable trim pot across there, repeat the process until that drops to a half, and then measure that resistance to work out what value it is, and then using that particular transformer you had, work backwards to try and work out what the proper collector impedance was, and then rewind a second transformer to now match that to 50 ohms. It's a bit of a long-winded explanation there, but I found this process here pretty straightforward, and got the result that I wanted. And CE there, that's our emitter bypass capacitor. As I mentioned before, I'm going to play around with that one actually in circuit to try and maximize the gain between 80 and 40 meters. So the actual amplifier itself is here. Hopefully I can keep this in focus if I don't go too far in. So we can see here our input, so that's our coupling, so again our transformer, transforming our 50 ohms up into the input impedance of that particular transistor, and our output transformer there. I had a couple of these just lying in the junk box, which I just took a few windings off, that's why the colour is different. But it still serves the same purpose. So that there's our collector transformer, as we saw before, sitting in there with 15 turns on the primary and 6 turns on the secondary, and then sitting across that is our 51 ohm resistor, you can just see there, to ground. Interesting enough, so in terms of the actual scope itself, excuse me for the jerking of the camera there, so that's sitting on 7.1 megahertz, and that is producing 21 dB gain, and I'll talk about that in a sec. And then as we come down in frequency, we can see it's slightly growing there at about 5.6, and then starts to drop back down again into the 80 meter band. So that's down to 3.5 megahertz. So that was interesting, and that was exactly what LT Spice was suggesting, that a certain value of emitter, oops daisy, apologies there, a certain value of emitter bypass capacitor there would have a peak in the response. So what I elected to do is I ran through 3 different options for that particular bypass capacitor there. 1 nanofarad, 560 picofarads, and then 10 nanofarads bypass, and decided that the best option there was 560 picofarads, which, like I said, gives 21 dB gain in the 80 meter band, 21 dB gain in the 40 meter band, and if we had a band sitting there in 5 megs, then it would have a whole 28. So I think that's probably about as good as I'm going to get for such a simple amplifier there. And again, I make no real apologies for making sort of circuits relatively simple. You know, I'm not into, well, at this stage of the game, into sort of multi device amplifiers and the like, so just trying to keep things nice and simple, just to sort of get the basics down, and hopefully encourage others to sort of give it a go. And this should hopefully be suffice for the super hit receiver there. Anyway, like I say, so I think 21 dB across that frequency range for a single device is probably not too far off. Okay, well I'll say 73s there. I think that covers all I want to talk about. Again, thanks to Lars for that feedback on working out the collector impedance there. It was good just to remind me about that one and to sort of delve back into it. And that certainly paid off, because that assumption of providing 200 ohms wasn't necessarily the case that provided maximum power transfer between the collector load and ultimately our load there of 50 ohms. So that 50 ohms there is going to become, like I say, or I mentioned before, our bandpass filter input. Right, so probably not too much else to say there, so I'll say 73s, and I think the next steps will be to probably just throw a few things together, the parts that we've made to date, the various modules, and have a look at a direct conversion receiver, just to prove out that the amplifier is working, that the double balance mixers are working, that this amplifier is working. There's no reason why it shouldn't, because each individual component has been tested as a module. But let's put them all together, get a direct conversion receiver going, and then we'll look to modify that to introduce a VFO and a BFO, the crystal filter, and then building up those two bidirectional amplifiers, one for the input to the crystal filter and one on the output. So like I say, direct conversion receiver first, then we'll build up the two bidirectional amplifiers and convert that into a superhead. Anyway, enough said, I'm starting to ramble now, so 73s, and we'll see you next time.